So the final two equations that I'm going to deal with that are given to you in the formula and data booklet for AQA is v equals u plus at, and then v squared is u squared plus 2as. So the v equals u plus at is fairly straightforward, and that's going to be our starting point for both of these anyway. So if you accept that acceleration is change in speed over time and the acceleration is uniform, then change in speed is going to be your final speed take away your initial speed, or final velocity take away your initial velocity, divided by how long that took. So you've got acceleration defined as v minus u over t. If I multiply that out and rearrange for v, I get that at is v minus u, therefore v equals u plus at. Okay, so we've got an expression in terms of v, u, a, and t. Now, if we want one that doesn't have time in it, that has displacement in it, there's a way of doing that. And actually, this v squared u squared plus 2as, although it was in GCSE, you can't really derive it unless you've got some other of the equations of motion. So if I square both sides, I get v squared equals u plus at all squared. Now, those of you doing A-level mathematics hopefully will spot that I can't just square these. I have to actually multiply out them as if they were two separate brackets. And I end up with v squared equals u squared plus two lots of these two multiplied together. So that's u a t, and then this whole thing squared, a squared t squared. So I end up with that, and it doesn't look necessarily like we're approaching what we're looking for. But what's quite nice and quite neat is then you can say that if I pull out the 2a from this, I get that u squared plus 2a ut plus, now if I'm multiplying by 2, I now need a half here because I multiply by the 2 to turn it back to just 1, and we end up with at squared. Now, if you follow the previous video, we've just done that s equals ut plus a half at squared. So then I can substitute in s equals ut plus a half at squared, and I get that v squared is u squared plus 2as.